The chairman for this session is Dr. Silas Michailidis from Eratosthenes Center of Excellence. And please, we can now start.
Thank you very much, Eleni. Hello, everybody, and welcome to this last session of the first international virtual workshop of Excelsior. And I go straight in calling Mr. Antonis Hadjiantonis from CERIC, who will give the first talk entitled Remote and In Situ Sensing of Water Combining Copernicus Services with Biosensor and IoT Technologies. Please, the floor is yours.
Thank you. Thank you for this invitation. Hope you can see my presentation clearly.
Yes, it's okay. Yeah, now it's much better. You have full screen. Please, you can go ahead. Thank you.
Thank you very much again for this invitation. If you would allow me to start with a short introduction about our company CERIC. We have been supporting Excelsior and Eratosthenes Center from the beginning of this inception, and we are very honored to be joining this very esteemed panel and workshop to present our collaboration also with Excelsior and hopefully with the space community in Cyprus. So very briefly, some words about our company. So CERIC is it's an SME. It's a small company based in Cyprus with our headquarters here in Nicosia. So we are operating as a research and innovation center, private research and innovation center, with the mission to support both the local ecosystem as well as enterprises and the public sector to promote innovation in Cyprus. And we are also recognized by the European Business Network as an EU big business innovation center. And this is one aspect of our collaboration with Eratosthenes Center of Excellence through our owned incubator, Gravity Incubator. We are ready to support the activities of the Center of Excellence towards bringing them to commercialization and also supporting startup researchers and all the great things coming out of Excelsior. In my role at CERIC, I am the manager of the Electronics and Networks division. So some of the aspects I'm going to discuss today are about the intersection of the in situ and the remote sensing part. And this is primarily based on one of the key sections of CERIC in our recent innovation portfolio. The central area, you can see here, the Internet of Things and Biophotonics is one of the areas we are leading both in Europe and Cyprus, of course. And this has to do mainly with what we call the Internet of Things, connected devices and all the sensors that we could use for the in situ part. And this is combined with a more, let's say, advanced sensing technologies, the biophotonic sensors I will explain in a while through some of our projects. And these are coming together to support the in situ part. So as I said, CERIC is a very active private research center. We have been active since FP7 and the Horizon project, with also being active as coordinators of ICT projects in the photonics, the robotics sectors. And I'm going to talk about some of the projects we have worked that relate to water sensing. So as it was mentioned also from previous speakers, when it comes to remote sensing, there are several challenges ahead, and the scale of sensing through the satellite is definitely outstanding, but there is some weak points where we would like to see the in situ part supporting and and let's say enhancing the remote sensing approach. So this quotation is from ESA website, where here we're referring to the problem of harmful algae blooms or cyanobacterial blooms. So as you can see, it is visibly, let's say, evident, and also you can process, of course, with several other of the remote sensing techniques to actually understand the composition and also the concentration of this cyanobacteria, for example, or this hub, the blooms. There is, however, the issue of how do we classify these blooms into toxic or non-toxic. It's not something that can be easily done from the remote sensing alone. And what is typically happening now is you will need to do lab analysis of water samples. So this is an area we have focused as CIRIC in the area of water sensing. We have been working the last 7 years on water analysis innovations, starting from the project Maria Box, which was funded in FP7, and we coordinated this project until 2 years ago when it was concluded. So this is about the marine environmental analysis, the in situ assessment of the water body, the marine waters. And newer projects we have been coordinating as well is Water Spy. Again, is another technology of photonics. And a more recent one, also in collaboration with CUT, is the Cyanobox project, which I will briefly talk about each one of them in the next few slides. So this is the one of the biophotonic part of in situ water analysis, which could be potentially very helpful in accurately determining what you are looking from the satellite and understanding better what is the composition. I will start with this project called Cyanobox. This is a local funded project in collaboration with Cyprus University of Technology. And as I mentioned, this is specifically targeting the harmful algal blooms of cyanobacteria. This specific project is about inland water and inland water bodies, so lakes, dams, and anything with that could be detected. And this is a project in progress now. We are developing this prototype, which will be an autonomous device installed in different, let's say, key locations of your water body. And the aim of this project is to automatically do in situ analysis of the water column. And as we are targeting some specific cyanotoxins, which are harmful for the human health, and also will be included in the renewed water directive for drinking water, like microcystins and saxitoxins. So this biosensor is able to determine the presence of these specific toxins and also to quantify this. So it's practically a mobile lab which can operate autonomously, and this is the value when you have remotely sensed a water body like a lake. You could also have in selected key points such a device in order to both verify what you see from what you detect from the remote sensing, but also determine the toxicity of it, which is critical, especially for early warning and for preventing health hazards. Another area we have worked on, as I mentioned, the Maria Box FP7 project, which was funded in FP7 with 4 million euros. This it's a similar concept for an autonomous device, which was deployed in the sea for marine water assessment. And also in this case, some of the biosensed analytes like different cyanobacteria and toxins were detected in order to assess the condition of the seawater. This project, as I mentioned, is concluded, and that's we are in the process of following up and making use of these technologies. The third project I would like to speak about is it's a Horizon 2020 project that CEST coordinated from ICT Photonics program, and this is it's a photonic device for drinking water. So this is a device that would be into drinking water reservoirs or pipelines of processed water, and the principle again applies. It's a different methodology to detect, but the principle of biophotonic is also evident here. So as I mentioned, since our work on biosensing and IoT is converging, let's say, on the ground section of sensing, this is more or less the bigger picture, or let's say the vision of how we see CEST engaging in this exciting sector as newcomers to this very challenging and complicated field. We find our position on the ground section, on the situ part of Copernicus, and this is our, let's say, vision and our invitation for collaboration, both with the Center of Excellence and the partners here. I would also add, in this vision of the in situ part, we have seen some of these devices. They can cover all the range of water body management. So we could have water spine devices on monitoring drinking, the water entering the drinking water network. We can have cyanobox devices monitoring lakes, dams, and all these water bodies, the inland ones. And also in the sea, selected areas can be monitored by marine box. So these are, let's say, the high-end biosense devices. These high-end devices, which obviously it's due to the cost, you cannot have a massive deployment of this. This is complemented with another IoT in situ sensing aspect, which brings together the low cost and low power sensing elements, what we call LP1. So we are specializing as a company in LoRaWAN, the long range de facto standard for IoT. And this is already a technology we have deployed in Cyprus and testing in different cases. And the interesting case with LoRaWAN is that it has been tested by other partners and companies as in direct to satellite communication of sensing devices. So this is quite exciting because you can now have several and densely covered areas with in situ measurements, which can also directly communicate with satellite to give you the values you need to calibrate or correct or verify the models you have from the different Copernicus services, like the land service, land monitoring service, and the marine service. So,
Mr. Kajandonis,
yes,
you have only 2 minutes left.
Okay, great. Yeah, this is
Thank
my
you.
last slide. Thank you. So I would like to conclude with this slide, which, as I mentioned, it's both a vision and a call for collaborations from our side. As I mentioned, we have built our capacity on the in situ and low power sensing element, and also adding the high-end devices of biosensors, which can give you very accurate in situ, actually lab measurements to really identify any dangers or any upcoming blooms that could be potentially dangerous. So that's all of that I would like to present. Thank you very much again for this opportunity, and looking forward for doing more with Excelsior.
Thank you very much. As we did before, we will collect all the questions at the end of the session, and I will direct them to the appropriate speaker. And I now call the next speaker, Mr. Markus Knopp. I don't see.
Yeah.
Ah, you're here. Okay. Hello,
I'm
good afternoon. Yes, yes, of course. Very nice.
I'm not sure how well it works with the video.
Yes, we will give you some instructions. Let me state your presentation title first. It's on optical communication from space to ground. Now, to the left corner right, to the left lower corner, you have a start video button.
Yeah, I think
you already did this, but maybe
you did that, yes. So the next thing is to share screen.
Yes, just share screen. It's just the settings of the computer. You can do it without the virtual background. It's fine.
Yeah. Okay, this is fine. Yes. You can proceed, please.
Do you see my screen now?
Yes, perfect.
Do you see the presentation, if I may ask?
Yes.
Oh, yeah.
Yes, perfect, perfect. Yes, okay.
Good. So then let me start. Many thanks for giving me the opportunity to present this, from my perspective, highly interesting topic to your distinguished community. I think you're at the point where you are taking decisions in to what direction your Center of Excellence is going to develop. And I hope that I can maybe deliver a slight idea of what could be interesting for the future, which is, from my perspective, optical communications from space to ground. And I will start with this introductory slide, why we think optical communications in space make sense. Status quo in RF communications at the moment looks like this, that the RF spectrum is a highly limited resource. So at the moment, you have to go through the hassle of getting licenses from ITU, and in the end, you will end up with a limited bandwidth to get your data down from Earth observation spacecraft to a ground station. On the other hand, instruments are developing further, and we are at the moment at a situation where instruments are gathering a lot more data than can be transferred to ground. So lots of raw data actually is thrown away already at the spacecraft because there's this bottleneck of RF communication to ground stations. And therefore we believe that optical communications could be a complementary technique which has some unique factors like high data rates, which are in the order of terabits per second to be downlinked. You do not have this frequency regulation hassle, so interferences are basically not present at all. The beams are very, very narrow, and therefore you do not interfere with other communications. You do not have to coordinate those bands like you are used to in RF communications. And of course, it's lightweight, also due to the narrow beam cone. Yeah, you can achieve high downlink data rates at a much lower, I would say, power consumption, but also volume and mass of the payload. So the field, in principle, distinguishes three different application scenarios. The first is inter-satellite communications, which is here named as a data relay market. The blue connections of satellites connecting. I'm not sure whether you can see my mouse, but it would be from here to there. This is something which is already existing. It's in operation, so to speak, with a European Data Relay System, EDRS. And Copernicus is somehow the prime contractor of this data relay service managed by Airbus. And to my knowledge, the Copernicus mission was able to increase their data throughput by 50%. So they get 50% more data down than they would just using classic RF direct-to-earth communications. At the moment, the scenario works like this, that there's this optical inter-satellite link to a relay satellite in geostationary orbit, and from there we downlink the data via classic RF channel. And this massive increase in data throughput is not necessarily due to the optical carrier frequency, but mainly to the usage of a relay system. Nonetheless, the connection, the inter-satellite link works at 2.6 gigabit per second already. Next thing, the constellation market. I'm sure you are aware of these mega constellations somehow aiming to bring broadband communications to remote areas. For them also optical inter-satellite links are of interest because they have to interconnect their satellite constellations. We at the moment are focusing on this third thing, direct to Earth market. So the classical picture of an Earth observation satellite which downlinks its payload data to a ground station. And for that, there are a number of terminals which can be used. I'm showing you here first the DLR terminal, or terminals developed at DLR, the colleagues from our Institute for Communication and Navigation. Two of them are already in orbit, OSIRIS version 2 and OSIRIS version 1. They are working, and I have to admit they are experimental platforms. So at the moment they are there to verify the technology to show that, that it's working. The OSIRIS 4 CubeSat is something which is going to be launched by the end of the year. So the space terminals are miniaturized already at the moment. You see here, this is a third of the cube is going to be used, 250 grams of payload mass, and only 8 watts of power consumption. And with that, they are already able to transmit 100 megabits per second, which is for CubeSats incredibly large amount of data rate. At the moment, they're using S-band communications and are sometimes limited to even kilobits per second. And the next thing, well, DLR is going to launch by beginning of 2021 is the further development of this OSIRIS terminal series, OSIRIS version 3. And this one is going to implement CCSDS standard on O3K is the name, optical on-off keying, which is the modulation format used to downlink this data. And here they are already going to implement 10 gigabits per second downlink. I have to add this is still with one frequency. So if you then dig deeper into all the tricks which are already used in RF communications, you can boost this to what I mentioned at the beginning, 2 terabits per second throughput, multi-wavelength, multipolarization, and so on. This is just the first step. The terminal is going to be implemented at the Bartolomeo platform, which is an addition to the Columbus module of the International Space Station. And here in the image, you see this boom. It's going to be located here at this boom. These boxes are experimental racks where users can bring up their own space hardware, sensors, experiments, name it, whatever you want to bring up there. And it's going to be installed via robotic arm. And then the user data is downlinked via this optical terminal. But I do not want to focus on DLR technology only. There are other manufacturers in Europe. For example, Thales Alenia Space Switzerland. They have a terminal Optical, which is also going to get its in-orbit verification by the end of this year, hopefully. And a relatively new commercial endeavor, FSO Instruments from the Netherlands. They are also building a CubeSat terminal, and this is even transmitting data at 1 gigabit per second at CubeSat size. So it's again less than 1 U. The terminal itself and power consumption is relatively moderate with 15 watt peak consumption. There's not so much difference to an RF ground station communication. So this is the downlink scenario. The satellite, once it's coming over the horizon, needs to be acquired. So the ground station shines light to the satellite. The moment it sees light, it's going to orient itself towards the ground station, and then the tracking and communication phase can start as long as the satellite is visible. You can downlink your data, which is on average, depending where the ground station is located, something between 5 and 8 minutes, I would say. And at the end, when the satellite fades away, again, going down under the horizon, of course, the link terminates. And this is the time where the communication also stops. In this scenario, you have some challenges. So one of the main challenges is the atmosphere itself. So the so-called index of refraction turbulence deteriorates the signal on its way through the atmosphere, which in the end means that you need to implement some forward error correction. But this is something where the colleagues in the last decade, I would say, have put much efforts into, and this is now reliably working. First experiments with flying laptop and virus to some extent show that this is not a problem in that sense anymore. And of course, the link distance varies along the path, but also between different passes, depending on the elevation of the spacecraft. And for that, the robust transfer schemes at the moment need to be implemented. And this is this optical on-off keying, which is basically an intensity modulation, where on the receiver side, then you can work with direct detection. This is this abbreviation IMDD, intensity modulation direct detection, which is which can work with a large dynamics, I would say, of the on the receiver side. Of course, this is what all of you have in mind as potentially the highest obstacle for optical communications, laser communications, the availability of the downlink due to clouds. And here I show you an image of NASA, which depicts a 30-year average of cloud cover statistics. The darker the color, the less cloudy it is on average. And yeah, I mean, in Europe, at least here where we are in the middle of Europe, in Germany, it's probably not the smartest idea to locate an optical ground station, because I would say 60% of the time you're gonna see a cloudy sky. If I look outside today, is exactly that case. But it gets better the more you come to the Mediterranean, and I will show you some data of Cyprus in 1, 2, 3 slides, which might be interesting for you. Now, to circumvent this obstacle of clouds, which basically block the optical signal, this is one of the main drawbacks compared to RF, because radio frequencies do not care about clouds. You have to mitigate this by the implementation of a ground station network, ideally a global network. So this is more or less the far goal we want to achieve, to have a couple of ground stations distributed at locations where the weather allows, I would say, 70–80% of the time to downlink some data, to have this direct visibility to the spacecraft.
Marcus?
Yes?
Excuse me, you have another 2 minutes, please.
Yes, okay, I'm gonna make it. So yeah, to cut the long story short, then here we have to focus on Europe, because this is what is of interest for us. This is where we can have a handle on. And we have identified different spots where the weather is comparably nice. Here, the blue color gives less cloud cover. The red colors gives more cloud cover. So it's the same map as from NASA, but in a different color code. And we have identified some regions where not only in summer and winter, but also in spring and autumn, cloud coverage is moderate. And with this information, ESA, DLR, and the commercial company CEST have set out to initiate what we call a nucleus of a global network. So we want to contribute as Europe a couple of ground stations which are able to communicate with LEO satellites via laser comms. This is just the same thing, but as a graph. I will cut it short here and show you instead the station availability in Cyprus. So I'm sure you're highly interested in Makarios, or at least some of you. And you see that in Cyprus, it's more or less the same picture in all the three spots we've chosen here. So again, on the y-axis, we see cloud fraction coverage in percentage. And the less cloudy it is, the higher is the availability. And during the summer month, this is really incredibly good. So below 10% of clouds. In winter times, it's on average a little bit, yeah, I mean, it's at least 50% here in Makarios. So it's also not so bad in winter. And from that perspective, here is the overall station coverage. If you take the average over the year, it's for all three stations round about 71% availability. And this is a very good spot, very good sites. I think here you could definitely contribute something if you were interested. Another thing, it's not only visibility due to clouds, but also to the spacecraft. And if we take the International Space Station as a reference orbit here, you see that you are rather complementary to Tenerife, where ESA is going to locate an optical ground station. We as DLR are going to Almeria. The reason for that, I mean, we can go into detail here if you are interested. The main thing is there's an overlap with the station in Almeria, and we want to do some experiments where we hand over an optical link. And this is my last slide. So this is the project where I'm lucky to be the project manager for it, the free space optical ground antenna Tabernas, we've called it. It's going to be an optical ground station remotely controlled from our premises in Weilheim. As I just mentioned, it's going to be located in Andalusia, southern Spain, at Plataforma Solar de Almeria, which is a solar research facility where our colleagues from DLR for Solar Research do already operate a meteorological station. And for that, it was very good to cooperate DLR internally. This is the main reason why we went there, next to what I just said, this handover option with ESA. So thank you very much for your attention, and I'm happy to answer questions after the session.
Thank you very much, Marcus. We collect all the questions at the end. So now we move straight ahead to the next speaker, Mr. George Boustras. Yes, and the title of the presentation is Critical Infrastructure Protection, the Interface Between Safety and Security. Please, Mr. Boustras.
Thank you, Dr. Michailidis. Thank you very much. If you allow me for a second. Yep, can you see my screen now? Okay, perfectly. Well, thank you very much.
Perfect, yes.
Thank you very much, Chair. Thank you very much to the organizers as well. I see how many people are following this extremely interesting workshop. I have to say that I'm amazed. You know, the number of attendants is very high, and I would like to congratulate the organizing committee and you, of course, as chair, as well as the rest of the speakers and the attendants. This is quite an achievement. Anyway, I'm not going to spend too much time because I see that you are performing as a good chair and you keep the time, which is very strange and very good, of course, time management. Let me just give a very quick outlook of what we do. I come from the Center for Risk and Decision Sciences from European University Cyprus. We're around 20 people, 20, 21, 22. It depends, you know, like on the time that we count each other. We keep on growing. We have been around since 2016, and we have been lucky enough to have collected so far over 4 million euro from European Union competitive funding. Extremely happy that this year, especially happy and extremely, to be honest, stressed as well, because it is the first time that we coordinate two Horizon 2020 proposals, both under the security pillar. One has started a month ago, and admittedly, I have to submit a deliverable later today. I hope I will manage to. And the other one starts in September. We have been active in FP7, Horizon 2020, DG Eco, DG Justice, DG Home, Research Promotion Foundation, and many other things. This is a time for anyone that likes colors and this. I know that everybody likes this slide. That's why I always put it up there. I'm not going to talk about it. If anyone is interested, they can see that later on. I would like to say something about Eratosthenes and about Excelsior, of course. Together with Excelsior, we have, I think, with the leader of Excelsior, with Theofados Hatzimitsis, we go a few years back. And I think we tried, both of us, hard to create opportunities to collaborate together. We have a few projects together. And one of the projects that we are currently running is called Myrtis. This is actually from the organizations that you see involved. I think it is the only probably project in Cyprus that involves so many universities and so many organizations as well. It is a very current project because it deals with COVID-19, and what it is, it gives an early warning system as well as many other features with regards to COVID-19. This is groundbreaking. This is not under development, but it has been developed. Of course, there are many more features to come up, but as I say, this is watch this space because there is going to be many more things happening. Now, let me go to what I have to discuss with you today. I'm going to take you a few miles far from where you are now. I left everyone flying from the space in the previous presentations, and I'm going to ground you down to planet Earth, and I'm going to talk about our area, Southeastern Europe, and I'm going to talk also about what happens in the ground and how all this can relate and present what we do. I think many of you are familiar with this area, which is a very beautiful area. So many nice songs written about our area. At the same time, a very troubled area, admittedly. An area that, apart from the beauty that I have described, it has natural hazards. I am just naming a few in my slide. The Solea fire in Troodos in 2016, the Mount Carmel fire with 63 people dying, if I'm not mistaken, in 2016 or 2017, if I may. The Mati wildland urban interface fire on the outskirts of Athens with 102 people dead, and the Lebanon wildfires of 2019 with quite a few people dead. We have man-made disasters. 2 days ago, we celebrated, unfortunately, a very unfortunate day for Cyprus, the big explosion in Mari, close in between Limassol and Larnaca, where 13 people died in the biggest explosion and one of the biggest blows in the national economy within a day. I'm going to talk about this in a minute. On top of all these risks that I have described, the man-made and the natural risks, and I'm talking about risks because as I said, I come from risk group. We have climate change. The last time I couldn't use the background because apparently my window is too bright. And I see from my window a temperature of 42 degrees. And this is not the first day. I think it is the 10th or the 11th day this summer that we have surpassed 40 degrees. The way that things go, not because I say that, I think it is established scientifically. In 20 or 30 years, 85–90% of Cyprus will be deserted. And I think only areas in Troodos from 1,000 meters and above, they're going to still have some sort of life. So we're not doing well in this one. This is an added risk. We have oil and gas developments. We have developments, real developments in Israel. We have discoveries in Cyprus already too. We have the beginning of a campaign in southern Greece. And also we have Egypt with a huge natural gas depot, which is a blessing in disguise perhaps, but an extra risk as well, perhaps from a geopolitical point of view. And in addition, unfortunately, I was reading recently a newspaper or something, I don't remember which was it. It was a big one. And basically it said that it had Europe, North America, and then Southeast Mediterranean. Unfortunately, COVID in our area, thankfully not in Cyprus, is blooming again. So we have different cultures, but apparently we have the same attitudes, because risks and how we deal with risks has to do also with the human element and with our attitude against that, and I'm going to explain this in a minute. So I described some risks above. Imagine all these risks combined, all these risks perhaps leading to a systemic risk. If you are looking for a systemic risk, look at what is happening in Serbia now, with all due respect to the Serbian government, which I respect a lot for the effort they make to bring the country close to EU. COVID has become a systemic risk. And in addition to that, we can see some of the risks that I have described above, perhaps some combinations of them portrayed as combined risks. So there you go. Our area is full of nice things, but it also full of risks. Okay, I've said that perhaps, like in layman's terms, as a scientist, I have to present some data. And I was looking at my papers. This is a very important paper for us that were involved in societal safety. It is the paper of the Tixier, Dusser, Salvi, and Gaston. I know some of them, very nice guys. 62 risk analysis methodologies for industrial plants. It was published in 2002. 62 in 2002, in 2020, there must be 162. And in fact, I'm trying to write a sequel of this paper. I've been writing this paper for 3 years, and every time I'm about to submit it, I do some more research and I find another one and another one and another one. Anyway, so what I'm trying to say here is that not only we have the risks that we have, but we have too many tools for the problem. And as I said, a typical example of what can go wrong in critical infrastructure, usually for us here in Cyprus, for Cypriots, the problem that we have is that when we teach or when we make presentations, we look for examples that happened outside Cyprus, big accidents, especially in my area that we are interested in accidents. Unfortunately, we're looking for Chernobyl and all that. We have our own little Chernobyl, which was called Marie. Back in 2011, as I said, 13 people dying, was dramatic itself. What the consequences were for those that stayed behind were the following. And what are these consequences? The fact that we had a cost to the annual GDP of Cyprus of 2.83 billion euro, which is around 20%, if not more, of our annual GDP. All of a sudden, overnight, let me make the correct move, it went like this, 20% of the annual GDP, and on top of that, 70% of the electricity producing capacity of the island. Amazing. A catastrophe, a real catastrophe, a big-time catastrophe. The definition of a critical infrastructure protection accident, a definition of cascading events that happened after the explosion. I have a very nice film. I don't have time to show you. So a CIP can affect society. And in a paper that we have written, and I'm not gonna talk about this paper very much, I'm gonna say I'm gonna copy from a newspaper from the Evening Standard in 2009. It says that hundreds of shops across Southeast London and North Kent were forced to close, and commuters were left out, described incredibly frightening conditions on the roads as traffic failed. This was because a main electricity producing substation, not even the plant was working well, was looted by youths for copper, and everything collapsed. What I'm trying to say here, and perhaps in dramatic terms, is that we live in a world of risks. Unfortunately, the way that we build our capacity, our resilience against these risks, sometimes is faulty. And there are so many overlaps. And what are these overlaps? A, there is too much legislation. I was in a World Bank mission 2 years ago I think this is the correct verb, trying to assist the Greek government, the Hellenic government 2 years ago, to modernize the fire service. We needed to create a risk assessment form for licensing. And the amount of legislation that we had to face was enormous. I was really scared. Too much legislation, everything is done to protect our society, but our society is not present in this process. The current dogma is directed at having maximum power and no capacity, maximum capacity at more or less any given moment. And we empower the state in order to protect the citizens. And what the citizens do is what we actually do today. We watch from a screen. If you go back, yes.
Excuse me, you have another 2 minutes.
I'm finishing very soon.
Okay, very good, very nice, thank you.
We have, as I said, like the society not present there. At the same time, we have to decide on if we go for prevention or suppression. We spend so much time on suppression, and we have to go to prevention. And prevention includes all the technologies that Excelsior advocates. And another element is that the fact that we give so much we give so much focus on infrastructure when we talk about critical infrastructure, but we don't talk about the human element. There are more than 100 projects funded by the European Union. Very few of them looked at the human element. All of them looked at the infrastructure. And before I thank you very much, I would like to invite you. Excelsior is an integral part of the Nicosia Risk Forum that takes part every year in the second part of November, and we hope to see you there. This year we're talking about regional societal safety and the efforts to make people understand that catastrophes know no borders. Thank you very much. Sorry if I have taken some more time than I was supposed to.
This is just fine. Dr. Boustras, thank you very much indeed for the interesting talk. As I said before, we collect all the questions at the end. So we proceed to the next speaker, Dr. Skevi Perdikou, who is going to talk about landslide monitoring and risk assessment in Cyprus. Please, the floor is yours. Can you unmute your microphone, please, so that we can hear you? That's fine.
Okay, can you see my presentation?
Yes.
Okay. Can you see
Yes, this is just fine now. Yes, excellent. Okay. Thank you.
Thank you very much. My name is Skevi Perdikou. I am from GeoFem, and I would like to thank the organizers for this excellent workshop today and for giving us the opportunity to present our work here. And we look forward to further collaboration with Excelsior and the great work they are performing there. So my presentation today will be on landslide monitoring and susceptibility mapping. So I'd like to start with a few words about our company. We are an SME, and we specialize in a rare combination, actually, of civil engineering and Earth observation, which might seem a bit unusual, but I will show you through my presentation that these two go well together, and they can actually be used very effectively in order to not only perform analysis using satellite Earth observation, but also to give meaning to the results using our civil engineering expertise. So by combining this expertise, we provide informed, cost-effective infrastructure asset monitoring remotely, and our vision is to keep infrastructure safe for society by monitoring its health effectively and economically. So I'd like to start with the basic principles of INSAR. INSAR stands for Interferometric Synthetic Aperture Radar. So radar, as opposed to optical, is an active system, meaning that it sends out radio waves and then records the reflected wave from the target. Because it does not rely on the sunlight, that means that it can take measurements both at day and during the night, and it can also work under different weather conditions. The main measurements we make using the SAR is the amplitude of the reflected wave and the phase of the reflected wave. And I would like to explain here the phase difference, because we are dealing with phase difference in order to be able to measure displacements, movements of the ground and the infrastructure. So what we can see here, this is a satellite passing over a surface of the Earth's surface. So it sends out the radio waves. We can see here pass 1 is the solid line hitting the ground surface, which is originally at this location here shown as dotted line, and then the radio wave is reflected back to the antenna. A few days or weeks later, then the satellite passes from the same position, sending out radio wave on the same part of the Earth's surface, but in the meantime, the surface has subsided. So its new location is now here. So we can see here that the reflected radio wave is shown in dotted lines, in dashed lines. So what we can see is that comparing the first pass with the second pass, we can see that there is a phase difference. So this phase difference is converted into displacement and allows us to measure how much the ground has moved. This has to do with the wavelength of the satellite, depends on the wavelength of the satellite. And I'm not going to go into too much detail, but the sequence of the color pattern here, you can see blue, purple, orange, yellow, green. So this sequence it shows us whether we have an uplift or whether we have a subsidence. So we have an uplift if it's moving towards the satellite. So if this is the sequence of the colors appearing, or subsidence if it's the opposite. And also the colors show an indication of the magnitude of the measurement. So we're near the 0 here, and as we are moving, we have a greater movement, displacement. And this is a very basic principle of INSAR, which compares only a pair of radar images. But of course, we perform a bigger data set in order to have a millimetric accuracy of our results. We also have ascending and descending geometries, meaning that when a satellite is orbiting in an ascending geometry, meaning that it's in a northward, moving from South Pole to North Pole, like this one here, and it observes the spot on the Earth's surface from west, while descending orbit is when the satellite is moving in a southward direction, moving from the North Pole to the south, and it obtains the data, the same part of the Earth's surface from the east, of course in an oblique direction with radar data, satellites. So when we have ascending and descending data of the same part on the Earth's surface and the same target, we can analyze this and decompose this into true horizontal movement and true horizontal and true vertical. Of course, horizontal on the east-west direction, or in a customized direction if we know the true, if we're interested on a slope, if we know the real slope of our surface. So now I would like to show you our specific project on landslides and the importance of recognizing a problem before the landslide occurs. So if we recognize the problem before it occurs, the majority of losses could have actually been avoided. So it's really important. We have performed a susceptibility analysis in the area between Paphos and Limassol that will show you in the next slide. And just to show you how big a problem landslides are in Cyprus, in 2010, a study by the Cyprus Geological Survey Department and Scott Wilson documented 1,842 landslides. This is only in Paphos district, and these landslides are extending over 134 square kilometers. So this is our area of interest. So as you can see, it's a bit more than 20, so it's about 30 kilometers by a bit more than 20 kilometers. It covers west of Limassol to Paphos, and a great majority of the great number of landslides detected by the Geological Survey Department are included in this area. And the methodology we used, we have used INSAR analysis that I just explained in order to determine the displacement of that area of interest, the movement, both horizontal and vertically. And we also accounted for controlling factors. These are factors that they could contribute to the occurrence or triggering of a landslide. We used hydrological factors like rainfall data from nearby meteorological stations. We used geological data from the Cyprus Geological Survey Department, the geology of the area. Topographical data as this determined from digital elevation models like the slope of the area, the aspect, meaning which direction the slopes are facing, which is an important factor because if it is exposed more to sunlight, then it's a drier area, which is, has a different impact to the landslide. The curvature, and also vegetation using optical data from Sentinel-2. Now, each of the classes of these controlling factors were assessed and evaluated against the INSA results using a weight of evidence analysis, and that helped us to produce a landslide susceptibility map. So for the INSA analysis, we used PS and SPAS. These are two techniques using a big data set. PS is usually used or it produces better results in urban environment and is more applicable for linear movements. When I say linear movement, I mean when we have progressive movements over time. And SPAS is usually performing better in rural, sparsely vegetated areas, and also performs well when we have non-linear movements, meaning that when we have seasonal changes, for example, from swelling clays that they can cause uplift and subsidence. And we use the data set for Sentinel-1 images between March 2016 to March 2018, using both ascending and descending data. And these are some of our results. This is a map showing the vertical velocity. So we can have values here from plus 35 to minus 60 millimeters per year. This is the mean annual velocity. So we have more than 6 centimeters of movement in 1 year in some areas. The coloring, because of the scale here, is not, it doesn't show that well. It shows better for the horizontal. Again, for the horizontal, we have between plus 76 to minus 86 millimeter per year velocity. Positive means eastward direction and negative means westward direction. So we have quite big numbers here. And the way we analyze this data is we have identified more than 9,000 points of movement. And these points were then divided into training and validation points in order to perform our statistical analysis, together with the controlling factors. Here are some of the results of these controlling factors. This is the first one, shows the rainfall. This is data from 13 closest meteorological stations. This one is the aspect, sorry, this is the direction of flow, and for this one we used slope and aspect data in order to produce a map showing the direction of flow. The geology of the area. These are, sorry, these are the slope, the first one. So you can see between 0 and 5 degrees, 5 to 20, etc. The aspect, which shows the direction of slope, and the curvature. And actually, we could, we identified which of these classes are important in the occurrence of landslides. For example, for slope, we identified that between 5 and 20 and 20 to 35, these two classes showed the highest correlation with the movement. And the curvature was also important.
Skevi, you have another 2 minutes.
Okay, thank you. Thank you. Susceptibility mapping, you can see here, that's what we concluded with. This is a susceptibility mapping showing us with red the areas with high susceptibility, orange, moderate susceptibility, etc. And we had good results with prediction rate of 79% and a confidence level for the high susceptibility area of 84%. So this is a very important result because what you can see here in black are the areas by the Geological Survey Department, but showing as a background is our results. So you can see that here we have movement, even though for areas that have not been identified as landslides in 2010. And here I want to show you what we have developed. We have developed a customized WebGIS platform which contains the susceptibility data and as well as the insert data, which are updated automatically whenever there is a new image every 6 to 12 days. What we can see here is a house which is on an area with no landslide, which shows very small movement or no movement. You can see here there's less than 5 millimeters or 10 millimeters over a 4-year period. And here actually is the start of a landslide. And you can see this house here suffers great displacement, nearly 3 centimeters over this period. So this is the start of the landslide. And monitoring of the road network, again, we can compare different parts of the road network, of the infrastructure, and see where the problems are on our road network. And I wanted to conclude with this one. I added this last minute because this is an area we monitor since 2015. This is the road network of Paphos. You can see here, we have identified this as an area of high displacement, showing nearly 3 centimeters, 30 millimeters of displacement. And actually 4 days ago, we have a sinkhole in Paphos here. So the concluding, we can see that INSAR is a very powerful technique for monitoring ground and infrastructure movements. Landslide susceptibility maps can be updated regularly because landslides are dynamic. I mean, they can be triggered after rainfall. So it's very important to offer up-to-date information or after a raining season or after the hot summer. And WebGIS platforms provide effective monitoring of infrastructure like the road I showed you, where we can take proactive maintenance where needed. These are my contact details, and I'll be very happy to answer any questions and collaborate with anybody on any interesting projects. Thank you very much for your attention.
Skevi, thank you very much indeed for the excellent presentation and the clear results. Yes, we have to move on to the next presentation by Professor Fedon Kyriakidis. The title is Offshore Wind Power Assessment Around Cyprus Using Sentinel-1 Data. Professor Kyriakidis.
I'm coming up. Can you see my screen?
Yes, if you can put it full screen. Full screen. Yes, please. Yes, please.
All right.
It's okay now.
Okay. I might have a problem with the camera, so we'll see how we'll get around this. Hopefully, it will not. I'm the director of the Geospatial Analytics Laboratory at CEST. I'm also involved in the Big Earth Data Analytics at the Eratosthenes Center of Excellence, and I'm serving as the research coordinator of the center. Happy to be with you, and thank you everybody for joining and staying up late for those who are. Our area is geostatistics, spatial analysis, and applications in GI science, remote sensing, and related disciplines, including public earth and archaeology. We all know that offshore wind offers an excellent opportunity, especially in certain countries, let's say Denmark or the Nordic countries, for domestic renewable energy production. And the offshore wind industry has grown enormously in the recent years, and it's reaching more and more capacities for production. Cyprus, on the other hand, is lagging behind this global trend. There are several efforts, few efforts on the land, but almost none on offshore wind farm projects. And one of the problems that are essentially hindering this is the very steep bathymetry gradient that essentially leads to very steep, deep waters, pretty close to the, relatively close to the shore with other countries. That makes even floating wind turbines marginally economical. So with this, we're going to see, we are developing essentially we have a project from the Research and Innovation Foundation of Cyprus to look at the integration of satellite data, mainly Sentinel-1A and B, with numerical weather prediction data, actually reanalysis data, specifically the WERA harmony from ECMWF. That project is focused on the integration algorithms and the statistical models. I'm going to talk more about the satellite data source alone and the picture it gives us about the offshore wind potential of Cyprus in a relatively small area around it. So I won't bother you with too many details. So basically, Sentinel-1A was launched in 2014, Sentinel-1B in April 2016. The level of resolution depends on the acquisition mode and the level of processing. There are three levels of data. We are using for this particular analysis level 2 ocean data that are already processed by a physical model to yield wind speed and direction at the 10 meters above the surface of the sea. So we were focusing on only the OCN data which for the region of Cyprus are available from June 2017 to June 2019. So these are only 2 years of passes. And I'm going to be showing you results with comparison to coastal stations, only 3 in this talk. We have results for several other stations around the coast from the service that NOAA is actually providing through the local services around the world. The different angles essentially of Sentinel over the passes make the information a little bit different at each pass. So we have to resample the data at a regular 1 kilometer grid to bring it to a common basis. We didn't extend that interpolation, essentially nearest neighbor interpolation beyond 1 kilometer to avoid extending the results in an area that is not much influence from the data. There are several quality flags in the Sentinel data from 0 to 3, 0 being good, 3 being bad quality, and they essentially reflect the quality of the inversion, of the geophysical inversion model. And we had discarded any flag values above 3. So the bad quality values. There are also some problems with the stripes along the edges of the adjacent tiles, and these had to be removed also. In order to make things more statistically robust, not that it's definitely guaranteed, we discarded values with nodes or pixels with values less than 65. In the entire span of these 2 years. So this leads us to about 475 maximum data at the point, which is close to this region orange here, close to Larnaca, closer to Larnaca actually. The Acrotiri region has fewer numbers here, and Paphos region has also fewer numbers. So here is some comparison with hourly data from 3 stations. Box plots on the far left, you see the actual data from the stations, and the next 5 box plots correspond to the 5 nearest Sentinel nodes. And so you can see that overall, there is a slight overestimation in the satellite data for those nodes, and that the satellite actually, especially for the Acrotiri area, has larger variance, essentially more variability, at least as the 0.75, 0.25 quantiles in the median are concerned. Here are the cumulative versions of histograms, the cumulative distribution functions for the data at the stations with the dark blue, and the nearest 5 CDFs for the nearest nodes of the Sentinel. You can see that the data from the Sentinel are more to the right, which means they're higher values in general, and are more also stretched out, which means that they have more variance in general. Here are some statistics of comparisons between the closest stations, sorry, the station data and the closest nodes of the pixels of Sentinel. You can see, for example, here the mean is about 390 for Paphos, median, the mean 4.34, that's speed, meters per second average over the entire span of the data. Criteria 4.1, Sentinel 4.3, Larnaca 3.72, and mean for Sentinel 4.89. And you can see the what I just told you before in some numbers, essentially in this table. Going to a paired comparison, so isolating values, dates or times where Sentinel are available and the station data have recorded a value no more than, I think actually there was two comparisons. This is for even no more than 45 or 50 minutes away from that time that you have Sentinel data. So they might not be exactly contemporaneous, but they are within some window. And we have done some sensitivity studies on that. Much closer in time, you have fewer data, of course. So this means that in Paphos, we have 131 data in common. Here you draw is the correlation coefficient, it's pretty high. The bias is the difference between positive means the higher Sentinel is higher, root mean squared error, and mean absolute error for these three station data. So here are, this is an overall estimation of the average wind speed and the of the Sentinel values at each grid node, at each pixel. And that's on the left, and on the right is the standard deviation of those data values at each pixel. So you can see the per pixel variability. Some areas below our criteria appear to be around the 5.5 meters per second region, but have a high variance, standard deviation. You can see because those numbers also to the right, those colors correspond to large standard deviations. Obviously, you can compute these on a different time basis, monthly or seasonal. And here we see the seasonal version of those values. Clearly, you can see that the winter is more windy, and spring is a little bit also. There is an area around again, south of Akrotiri Peninsula, southwest, where there are some values high in the winter and also in the spring. Autumn is also some, there are differences in the color scales, okay, because if we have a common color, then a lot of these appear blue, so just pay attention to the color bars. So basically winter and, and autumn are, and to a lesser extent spring are the most promising seasons for this data. So in order to go to a wind power assessment, we need to go beyond the data and essentially fit distribution models to those at each pixel. And here we've adopt the Weibull distribution, which is a widely used distribution in wind results assessment. There are others you can use. We tried several of those. They didn't differ that much from the Weibull. So it depends. The Weibull is characterized by two parameters, the scale and the shape parameter. The shape parameter essentially tells you the higher the value, the more concentrated the values around the particular peak are. So these parameters A and B are related to the mean and the variance, the classical moments of the distribution, but we talk in terms of A and B for the Weibull. So once you have adopted these theoretical model, and you can do that by searching in the literature or making goodness of fits test with different alternatives, you can go ahead with parameter estimation, which means that you want to find those values of A and B that minimize some measure of discrepancy between the theoretical distribution and the actual data quantiles or probabilities if you look in different axes. So here is an example of a fitting of a Weibull to some data represented as a histogram with blue bars. The same you can do with a cumulative version, the cumulative distribution. So here are the These are the empirical, the sample with blue are the station data, and with red, either dashed or red, are essentially the nearest station, or the nearest sentinel values. So you can see the same story. The Paphos data, the fit of the Weibull distributions to the data for the Paphos station is better, and the same holds for the to a lesser extent for the closest sentinel. So the closest sentinel fit actually deviates from the observer, which is closer to the data for that particular part between 5 and let's say 6 or 8 meters per second. So here we can see the Weibull derived mean and variance or standard deviation after you estimate the A and B coefficients of the Weibull distribution for the same areas as before. To the left, you can see the mean wind speed and the standard deviation as derived from the fitted distributions. And to the right is the mean and the standard deviation from the sample data. You can see that there is a slight, actually an overestimation of the standard deviation of the variability at the lower southwest of Akrotiri, in the lower left-hand side, as opposed to the lower right-hand side image. Once we have a distribution for the we had actually, so the goal is to actually derive average wind power density, which is an expression of the kinetic energy, the average kinetic energy passing through a particular unit surface over time. And it's one of the most used quantities in wind resource assessment. If we had wind speed series, which we do at the stations, we could just compute the average velocity cube and multiplied by 1/2, and rho is the density of the air. Unfortunate notation I used rho before for the correlation coefficient, I apologize. And the 2 minutes.
1.5.
1.5, okay. So the expression is, once you have the Weibull, you can compute simply by the gamma function. Here is the wind power density in watts per meter square for the region. So the A promising region would be southwest from Akrotiri, between Paphos and Akrotiri. And you can do the same thing with different seasons. Again, winter and spring are the two most promising seasons. And we can see a classification of what is favorable, what is good. So we could think of looking more into these areas down the road. Ongoing in future work, we will be incorporating essentially DTU's data, the Danish Technical University data that they've been releasing level 1 actually data for a long time through geophysical models, and extend the series back to the origin of the Sentinel. Our goal is to integrate the Wera harmony and essentially come up with a combination of the reanalysis data have a coarser spatial resolution but a higher frequency in time of sampling, and combine that with a finer spatial resolution Sentinel that has a smaller frequency in time. And we intend to look at different data sources and integrate those. Cosmo reanalysis 6 in the New European Wind Atlas, of course, and Sarah from Copernicus, and to have also an assessment of the uncertainty in the wind power estimation and how that might actually propagate to the selection of the potential sites for offshore wind farm installation. Thank you very much for your attention.
Thank you very much, Fedonas. Now it is my turn. The next talk is by me. I'm sure everybody can see my screen. I'm going to talk about measurement of rainfall from space-based platforms. I like the first line very much when I read about it. People more and more call this century, the 21st century, as the century of water. And the reasons are obvious. We have several problems directly related to the availability of water, especially drinking water, fresh water for people, but for many other reasons that water shortages on top of floods and many other hazards that some of the speakers before talked about it, make water a very important element as far as our existence, our activities, economic activities, social activities, etc. Rainfall is the major input to water resources, and this is what I'm focusing on this in this 10 minutes or so. And the rainfall data are important for many applications at different time scales. I'm not going to read through all of these time scales. Typically, rainfall is measured by using in situ instruments. The rain gauges that are simple instruments, basically measuring rainfall by collecting it into a bin, then measuring the height of the rainfall. And this is what we officially, at least, term as rainfall reaching the ground. There are something like 70,000 stations like this all around the world. You might think that this is too many. Nevertheless, if you collect all these stations, they can barely fit into 2 basketball courts. So this is an unacceptably low coverage of the entire surface of the earth. On top of that, you can add a number of other instruments like YOS distrometers, optical Parseval distrometers, ground-based radars, 2DVD distrometers, hydrophones, and a variety of other ground-based instruments. Nevertheless, still, all of these are not enough. So you actually need some other measuring platform, which preferably would be put much higher, ideally in space. From space, you can see the entire Earth. And in the past couple of decades, satellite precipitation measurements, I should better call it estimation, because the platforms from space do not really measure rainfall. We rather estimate precipitation, as we will see in a minute, rather than estimate it. So we passed basically through 2 phases. One by using passive microwave sensors, and you see the list of satellites that have carried into space such sensors. The sensors might be a little bit different. Nevertheless, the principle is the same. We measure with these microwave sensors reflected visible sunlight from cloud tops, or we measure the infrared radiation emitted from a cloud by using microwave sensors in space. Of course, you need some sort of translation, some sort of decoding of the visible reflection from the cloud and infrared reflection from the cloud into intensity of rainfall. So basically, with microwave sensors, we estimate rainfall rates. Another basic principle used in microwave sensors is that we can measure raindrops, amount of rainfall, by using low frequency channels, and also high frequency channels for measuring the scattering backwards of radiation from cloud. Again, you need some sort of decoding of the measurements from microwave measurements into raindrop sizes or ice particle sizes, and from there on into intensity of rainfall on the ground. The second and very important achievement through the last 15 or 20 years is by using active microwave sensors, that is radars. And the major breakthrough into this business is during the TRIM rainfall mission, the Tropical Rainfall Measure mission, in which NASA and JAXA, NASA from the United States and JAXA from Japan, have implemented to measure tropical and subtropical rainfall. This is the first slide satellite in space with a spaceborne precipitation radar. The mission was very successful. Nevertheless, it ended in 2015. This was the lifespan of the satellite, and the kind of instrumentation that was carried aboard this very important historical mission, one precipitation radar and also one microwave imager. These two instruments really made history, and I'm just displaying here a picture of Cyprus during one of the trim overpasses. Okay, I said already that this mission was completed in 2015, and the next follow-up mission is the Global Precipitation Measurement mission launched in February 2014, following the successful operation of TRIM. Again, NASA and JAXA was the leading agencies in this new mission, but this was complemented by consortium of international space agencies like one from France, Indian Space Research Organization, NOAA, EUMETSAT, and others. Now, the important thing about this new mission, which is still ongoing, is that the importance is that we have two groups of satellites. One is the core satellite that I will show a little bit of details in the coming slide, whereby this was supplemented by constellation of satellites that are using the traditional passive microwave radiometers. You see the picture of the core observatory that is in the core of the mission, the new GPM mission, which actually is in a position with instrumentation carried on board to give three-dimensional maps of storm structure. This is indeed a breakthrough regarding space technology for measuring precipitation. And although the tropical rain measuring mission TRIM was terminated in 2015, currently NASA is working towards merging the TRIM data with the GPM data into a single compatible data set. That will make this new data set a unique global data set with very high spatial and temporal resolution, covering the needs of several applications. And this is yesterday's global view from the new product, so-called IMERC, whereby you can see the entire globe with merged data from many satellites rotating around the Earth in an orbit around the Earth. So this data set is available now every half hour. Every half hour at a resolution of 10 kilometers, which really makes it unique, a unique database for rainfall. About satellite measurement of precipitation is validation of GPM data is an important aspect, because through the incorporation of such data, validated data into operationally useful applications will still make the GPM data a unique database. Cyprus is actually in an ideal position to contribute to GPM ground validation because nowadays the Department of Meteorology is operating two X-band ground radars that can measure precipitation horizontally this time, around 40 automatic rain gauges. 3D astrometers are operated by the Cyprus University of Technology, and around 140 daily reporting rain gauges. All of these, I think, make Cyprus a perfect candidate to contribute to the GPM ground validation effort. And the final word about all of these sources of rainfall data is that a more comprehensive cloud view, global view of rainfall can only be achieved by using all the available platforms, starting from ground radars, hydrophones, ground radars, ground rain gauges, distrometers, and the available satellite measurements from space. And I thank you very much too. Now I have to stop sharing the screen, and I have to call the next speaker, who is Professor Chris Danezis. Yes.
Hello there.
Hello there. And the title is Cyclops, Strategic Research Infrastructure Unit for Geohazards Monitoring in Cyprus and the Southeast Mediterranean region. Professor Danezis, please, the floor is yours.
Thank you very much, Silas. Hello there. My name is Chris Danezis, and I'm an associate professor at the Cyprus University of Technology and serving as the infrastructure coordinator for the Eratosthenes Center of Excellence. So my presentation revolves around Cyclops, which is a strategic research infrastructure unit for monitoring geohazards in Cyprus and the broader Southeastern Mediterranean region. I'll cut straight to the chase. Cyprus exhibits a significant seismic risk and very intense seismic activity. Apart from that, we have landslides, as Skevi pointed very well in her presentation. Severe landslides, like the case of the Isuri village, and many landslides, so many that we are not actually aware of the number because of the limited resources from the corresponding department, the Department of Geological Survey. So I'm not going to go through the direct and indirect costs that actually are involved in landslides. Their impact is quite severe in Cyprus as well. To date, 8 villages have been abandoned, not to mention the damage in critical infrastructures and, of course, potential damage for cultural heritage landmarks, their impact in tourism, most of all, and so on. Apart from that, the geodynamic regime of Cyprus is quite interesting. According to a latest paper that we published this year, it appears that Cyprus is moving towards northeast with a velocity of around 2.5 centimeters per year, which has an imminent impact on the mapping, the spatial data infrastructure of the country. Therefore, we can employ two most prominent space-based observation techniques, namely GNSS, which provide millimeter-level absolute displacement and velocity determination, but pointing at a single point on the physical surface of the Earth, and of course, synthetic aperture radar, SAR, which delivers centimeter to millimeter level relative displacement and velocity determination, but at a greater and with higher resolution. Let me go briefly through this slide. Okay, GNSS revolves around one-way signal transmission from space to ground receivers. It employs currently 3 frequencies for doing that. SAR, on the other hand, is an active signal, employs active signal transmission from space and the reception of the backscatter, from the ground. In the framework of Cyclops, 2 SAR missions will be mainly used. That is EU Sentinel-1 and TerraSAR-X from the DLR. With respect to the GNSS ground segment, let's say, what sort of receivers are we using to achieve this millimeter level deformation acquisition? There are many means to do that. One of the most crucial parts is monumentation. You can see here there are several monuments where the GNSS receiver may be positioned. In Cyclops, we go with high stability monuments with using the stringent, specifications available worldwide from UNESCO and the International GNSS Service. With respect to the SAR ground segment, we will be using corner reflectors. Pretty much these are artificial reflectors with zero radiation absorbance, and they're used to enhance the backscatter, the signal reflectance back to the satellites. one key element here is the combination of these two segments, that is, have corner reflectors and GNSS complement each other, which is what we are planning to do in Cyclops. This is another example of the determination of uplift of subsidence using Tesat X high resolution data. In the frame of Cyclops, we'll be using, as I mentioned earlier, global navigation satellite systems along with INSAR techniques through a technique well known as geodetic SAR. That is, GNSS will provide crucial atmospheric corrections and geodynamic related information to correct the SAR-derived ranges through corner reflectors. And by co-locating actually GNSS receivers and corner reflectors, we may actually produce centimeter to millimeter level deformation products on a continuous basis and at a higher resolution. GNSS, we know how to do this well. With respect to INSAR, we cooperate with one of the global in the field, which is the German Aerospace Agency. The infrastructure that we are going to establish in Cyclops was pretty much inspired by two main global infrastructures, globally known, infrastructures around. That is the GeoNet in Japan, which is a very dense network of GNSS receivers. It numbers more than 1,300 permanent GPS stations. And of course, AGOS in Australia, which is which uses both technologies, but not in a co-located fashion. So, what triggered Cyclops? First of all, the infrastructure for monitoring geohazards in Cyprus is pretty much limited to conventional equipment, that is seismographs, inclinometers, some sparse drills, and so on. There are two permanent networks in the country, but they're mostly using outdated equipment, and they do not use such a well monumentation, stable one, in order to use them in deformation monitoring applications. Furthermore, our coordinate reference systems and so on need to be modernized. And last but not least, there's a lack of an efficient early warning system, actually, to enhance preparedness and prevention by means of space-based information. Our consortium, actually, as I mentioned earlier, is the Cyprus University of Technology, us, DLR, and we have a strong support from the Geological Survey Department, Department of Lands and Surveys, the Electricity Authority of Cyprus, the Ministry of Defense, the private sector, and the European Plate Observing System itself, a European research infrastructure initiative, very important one, on monitoring geohazards. The objectives of Cyclops are pretty much the implementation of a novel integrated strategic infrastructure unit to monitor geohazards. We do this by addressing critical priority pillars of the national strategy, by enabling close cooperation with all the involved stakeholders through collaborating with the very best in the field, the DLR, in order to create a critical mass of researchers and become sustainable eventually in the future. All these are actually focused towards the implementation of the UN Sendai framework regarding disaster risk reduction, a very important framework that involves 7 targets, includes actually 7 targets to be achieved by 2030 with respect to disasters. If I can describe what's innovative in Cyclops, Cyclops will form the backbone for disaster risk reduction, may actually form the backbone for disaster risk reduction related research. This is a state-of-the-art actually infrastructure used for monitoring natural hazards. in the frame of which a novel early warning system will be used to integrate the most prominent space-based technologies along with other data I will explain later on. One very important aspect, as Mr. Silas highlighted in his presentation, is that through this infrastructure, Cyprus will actually promote the European constellation and not only, and will become a very novel calibration and configuration site for them. Furthermore, Cyclops can be the backbone for the national space data infrastructure and will augment and promote very important European research infrastructure incentives such as EPOS. To describe the system very briefly, it will be comprised of two main segments, two components, a multi-parametric network, which will be consisted of two segments, the permanent segment, which will include permanent GPS GNSS stations, weather stations, tilt meters, and the INSAR corner reflectors, and a mobile segment one, which will include actually a wide range of heterogeneous sensors for monitoring geohazards, GNSS stations, interference detectors, terrestrial laser scanners, UAS, and so on. Finally, the second component, which is the operation center, it will include three main servers, one to deal with the processing of the information, one to store it, and one to handle management tasks. I highlight here again the co-location of heterogeneous sensors. Regarding the permanent segment, as I mentioned earlier, a minimum number of 6 permanent GNSS stations that will be using the most stringent international standards regarding their monumentation and their hardware are going to be established in selected sites around Cyprus. And in every site which will pretty much make the permanent segment, apart from the GNSS receiver, an opposite facing corner reflector configuration will be used, actually 2 corner reflectors per site facing in opposite directions. In this way, we will increase actually, we'll have 50% more data for deformation monitoring. Now, the locations of Cyclops have been determined according to many actually discussions we had with the Department of Geological Survey. One of the most important aspects is to put all this infrastructure on top of solid bedrock. That is one of the most important requirements. And furthermore, we want to collocate further with the National Seismographic Network. That's another picture of the new the sites. That's a layout actually of the GNSS stations as they will be established in reality. We are waiting actually to receive this equipment by means of an open tender. And this is a picture actually of our corner reflectors, which give a great deal of flexibility in terms of azimuth and elevation adjustment through a sophisticated leveling plate designed by DLR. In this way, we can support not only one satellite missions, but more than one. For example, Sentinel, TerraSAR, Cosmos, SkyMed, and so on. And their actual image, as they have been received last week from Germany. Furthermore, we possess 2 latest, actually electronic SAR corner reflectors that they will also be deployed on site and be further validated as they are quite new nowadays. Regarding the mobile segment, the mobile GNSS stations and weather station and configuration will look like this one, as you can see in this figure. The mobile stations will be further complemented actually by UAS and laser scanners. Our UAS is pretty much drone, actually our latest drone acquisition is the EBX RTK, which is an operational model actually currently used by several army divisions around the globe, very reliable one, to perform 2D and 3D mapping and terrain modeling at 10 centimeter level of accuracy, as you can see. Furthermore, this sort of accuracy in the near future will be further augmented by using position corrections for from the stations, GNSS stations that will complement Cyclops. Our IT infrastructure, as I mentioned earlier, it will include two servers, a processing server and a management server, and a storage one which will serve as a storage means for all the information that is anticipated to exceed more than 500 gigabytes per month. Regarding the early warning system, it will provide real-time integrity monitoring and position information via precise positioning techniques, along with an atmospheric monitoring service. Furthermore, there will be an episodic event notification service which will send alerts to the involved stakeholders, and access to all these services will be enabled through the smart devices.
Christos, 1 minute,
yes?
please.
Yeah.
We have to finish. Thank you.
Yeah. Okay. Apart from that, we have ultra-precise position methodologies employed by using scientific, very well-known scientific software that we may reach sub-millimeter level accuracy using several techniques for that to monitor more local phenomena such as landslides. A combined GNSS and INSAR technique actually to perform the calibration and of the constellation, as I mentioned earlier. And last but not least, we are currently about to publish an integrated WebGIS platform which will show this information, which will disseminate all this information, populate displacement maps, hazard and risk maps, susceptibility maps, earthquake and landslide history services, critical information on critical geospatial information on critical locations, and last but not least, a rapid crowdsourced damage app, one app, cross-platform app that we have developed, and we will release it next week, God's willing. This will give the backbone actually to perform a wide range of state-of-the-art research, such as the creation of shake maps, very useful products, hazards-related AI-based models, and so on. In the frame of Cyclops, 3 case studies will take place. First, we're going to determine station velocities for the 2 national GNSS station networks and do some landslide monitoring in archaeological sites, and one in mainly Pissouri, but we may change. It depends on after consulting the Department of Geological Survey to perform a more up-to-date product. Thank you very much for your attention.
Thank you very much, Christos. Well, one of my duties as a chair is to keep the time. I think I did very well under the circumstances. Another duty is to monitor the questions that are put by people through the system. There were many questions, I must say. Most of these have been answered already directly by the speakers in writing. There are still a couple of them which I'm not sure whether they have been answered or not. Anyway, I will send all the answers to the interested participants. There is one that just came in for a question by George Georgiou regarding the possibility of monitoring the underground. Let me see the question because it's a little bit complex, a long question. Underground minerals. I think some answers can be given directly. Still, there is one more that just came in. The answer is by Daniel Serra. I'm not sure whether I can give the microphone to Daniel to answer it directly, but I will read it through. Is Daniel? I'm not sure. Anyway, I will read the answer. And Daniel says that in the case of gold, the presence of alunite on the surface can be an indicator, but this is far from estimating its real presence for sure in the exact location. As I said, many questions have been answered directly by the speakers. There is one more question by Pooja to Skevi Berdigu, and Skevi Berdigu will answer in live. The question is, what should be the minimum coherence threshold for analyzing INSAR results for reliable land movement detection? Skevi, would you like to answer, please?
Yes, yes, thank you for the question. You can, depending on the method, I mean, it's not just one number, it depends on different factors. For example, literature would tell you that for PS, you can use threshold of 0.75 or ESPAS threshold of above 0.35, but it also depends on the distribution of the data. So what I mean is depends on how many targets your analysis has detected, because you should not rely on, let's say, one target on its own. So the distribution, the number of distribution of targets is also very important for the reliability. Now, regarding the landslide itself, you have to use your engineering judgment as to whether, I mean, you cannot say 5 millimeters per year, is it a landslide or not a landslide? You should use your, that's why we say we use our geotechnical expertise on this in order to judge whether this depends on other factors like the creeping of the soil, and is not due to the landslide. That's why we analyze temporal images and see the behavior of the ground. And for our specific analysis, we included actually data that showed movement greater than 30 millimeters per year, velocity greater than 30 millimeters per year, to ensure we didn't include movements of the ground due to creeping or other factors. I don't know if this answers the question.
Okay. Yeah, thank you very much, Skevi.
They can email me if they have further questions related to this.
Of course, yes.
Thank you.
Follow-up is possible between the speakers and the audience. We are open to sort out any of these issues. I just have got a new question. The question is by Wessam Emad, saying that how can we represent the seabed from satellite images? This is the question. And if anybody from the panel wants to answer, just unmute the microphone and say your answer in live, please.
Yeah, maybe Gunther here. Maybe I can respond to this. I'm not sure whether this is referring to what has been done with radar, with synthetic aperture radar. Synthetic aperture radar, Sentinel-1, Terrasar, Cosmo, you name it, is very sensitive to the ocean currents and the ocean waves. And there's a physical effect that the wave height and the wave distance changes when waves go to shore. So when the depth of the ocean is going shallower and shallower, and this shallowness basically can indirectly be measured by the ocean waves to be seen in radar. So this kind of stuff can be derived from radar. And from optical, there's also some bands, I think also including Sentinel-2, you can use to some penetrate a little bit the water down to ground a little bit, and some don't. So from this difference, you can see a little bit near shore ocean depths. But again, this is just a few meters, if so dozens meters, but you cannot see the deep ocean ground, of course, but shore and coastal near bathymetry can be derived partly both from optical and radar as in indirect measurement, basically. You're not measured directly the depth.
Thank you, Gunther. Thank you, Gunther. Well, if there are any more questions, I am monitoring whatever comes in now. There are some thanks to the organizers saying thank you very much for organizing this workshop and to be in touch. If I don't see any other question, I just conclude this session and give the chair to the organizers. Thank you very much to all the speakers for this session and for all the people who said questions and received answers. If you still have any questions left, please send a message through the Q&A, and I'm sure we will be able to handle them. So I hand over to Theophantos Hadjimitsis. Thank you very much.
Thank you, Dr. Michailidis. We will now proceed with a general discussion, and Mr. Gunther Schreier from DLR will chair the general discussion. Thank you.
Yeah, thank you. We have not much time left. I think it was a great webinar with lots of information. And I guess the only way for the speakers or the listeners, let's say 79 are still there, would be through the F&A button. So it's still open. So if you have any question, what I would like to share with you is basically some wrap up of this entire day. And therefore I like to just open my screen. So if you see my screen, you see my screen?
Yes.
Yes, okay.
Okay, thank you. Just a little wrap up, and again, feel free to enter some more questions and some consideration in the the question and answer button. So some wrap up. What we have seen here is the first international virtual workshop of Excelsior. It was Zoom enabled. We had some glitches, but for the 110 plus participants, it technically worked basically fine. I guess we had some dropouts of audio, but otherwise we were fine. We had over 110 participants with all the core partners of Excelsior being there and giving presentation. We had the welcome of the government of Cyprus, and we have presentations by international companies, universities and research labs in entirely 28 plus presentation. It was a full and long day. I think we deserve a rest after this long day. We had a panel on plans and infrastructure. There were reportings about the data acquisition stations and some reference to the data acquisition station still to come. There were some companies and some other interest indicated to establish a regional near real-time service, or that such a station can serve for other satellite data mission operators. We had also a presentation by Tropos and others about establishing a remote sensing supersite for atmospheric and climate research. This is especially valid for being Cyprus a hotspot for atmosphere and climate. And we heard some specific issues on Earth observation data for the environmental challenges we have in Cyprus and the Eastern Mediterranean region, and for disaster mitigation, especially by NOAA. And this deserves and this needs data, Earth observation data. This needs these data and services to be distributed. So it's all about big data, data hubs and service hubs to be established. Of interest was the international perspective. We heard NASA being active not only in the United States or the Americas, but also here with international projects. I think Vince is already going back to bed. For him, it was about 2 o'clock or 1 o'clock in the night to join us. We have a couple of presentations from our colleagues in Israel, nearby Cyprus. I think the shoreline of Israel is closer to Cyprus than the shoreline of Greece, if I'm not mistaken. So the flight from Tel Aviv is just, I think, 30 minutes, whereas the flight from Larnaca to Athens is about 1.5 hours to 2 hours. So Israel is a natural partner to Cyprus and this activity. We learned about European perspectives, Copernicus services on security. We learned more issues about what Greek is doing currently with Copernicus and central data on several instances. And for me of interest, and thank you also for joining the colleagues from the Azores Earth Observation Lab and from Malta. I think it's of interest that a similar initiative in the Atlantic with the Azores and in the Mediterranean with Malta are going on. And though they were derived and born a little bit differently, and maybe they aim for different targets, but I think there's lots in common, and Azores and Malta and Cyprus should somehow get together to share their experience in this. And finally, we had many presentations on science and applications from various colleagues. Soil and agriculture was an issue, forest fires. We had several presentations on geohazards and how we can potentially use radar interferometry to monitor geohazards, landslides, and seismic activities. We heard about critical infrastructure monitoring. We heard energy, wind and solar energy, precipitation, and many more. I guess the slides will be made available for the audience on the Excelsior website. So having said this, I give back this presentation and go back to the general screen here. I just check, there are no more, there are no more big questions here. So from those who are enabled with microphone, any general remarks, maybe I make it in the line of the participants of the Excelsior program. And maybe I like to start with somebody from NOAA. Haris, you're still there? What is your impression of this webinar? Haris is there, but maybe he's still muted. Well, let me start with Fantos. Fantos, your general impression about the webinar and some words.
Yes, thank you, Gunther. I am very surprised and I am fully enthusiastic about the webinar. We stay here from 9 o'clock in the morning Cyprus time until 5:30 Cyprus time, 29 presentations. I would like to thank everyone, and especially the external speakers. I would like to express my sincere thanks to Eleni Louli, Maria Prodromou, Marios Zouvaras, George Levendis, and especially to Gunther Schreier, because we spent more than 2 to 3 months to organize this event. And I would like to express my thanks also to the chairmans, Gunther Schreier, Mario Zouvaras, Silas Michailidis, Haris Kondoes. And just to highlight something, when I check the statistics on the Zoom, except for the last 45 minutes, we have online more than 110 people. Just now we have 75 online, but we receive registrations, 320 registrations. Sometimes the people, they choose to follow specific sessions. I'm fully proud of this, and the journey has been started, and I would like to express my sincere thanks to all of the participants and all of the event speakers. Thank you very much.
Yeah, Fantas, I think this should be also the last words. Just to remind you, this very webinar should have been taken place in March in the nice town of Paphos, physically. Unfortunately, we have a global crisis which we have to face, and unfortunately, we hope that the RSTY, maybe Fantos or Kyriakos can say, will take place next year or the year after next, again in Paphos?
Yes, Kyriakos?
Yeah, Gunther, if everything goes well, yeah, we'll do the next RSCY in Paphos, but we're hoping that the coronavirus will not be here next year to have, so we can have any problems, and we can have everybody visiting Cyprus, and not only that, joining the conference, and we can have another event next year for the Excelsior project.
Yeah. And the advantage of such a physical meeting in Paphos in a nice hotel is that we would now go for a reception with a good glass of wine and drink and some snacks. And now everybody of us is supposed to go to his refrigerator and maybe take out a bottle of water or some snacks or whatever is prepared. Or as myself, I have to go to the kitchen because I have to fetch my wife from the train. She is going physically to work. She is a teacher. So I have also to stop now, and I wish you all a very safe and healthy afternoon and further time. And I hope that in the further 6 years to come for the Excelsior project, we will at the end have a very sustainable and successful center of excellence in Cyprus with all your help and with lots of international collaboration. So many thanks to my colleagues and many thanks to all the audience and speakers.
Thank you very much for an interesting and very fruitful webinar.
Yeah, and we hope to see you both all in person again.
Yes.
On Cyprus.
Well, everybody has
that the whole workshop has been recorded, and we upload all the 5 sessions in our YouTube channel, Excelsior YouTube channel, and follow our social media by tonight or by tomorrow morning.
Thank you, everybody. Thank you.
Okay, thank you very much.
Thank you. Bye-bye.
Thank you.
Thank you. Bye. Goodbye.
Thanks. Bye.
Bye.
Thank you.
Bye.
Thank you.
Thank you. Bye-bye.
Thank you. Bye-bye.
bye-bye.
Thank you. Bye-bye.